Okay, I'm going to try something different today. I'm actually going to add some commentary to the videos that I'm asking you to watch for today's assignment. Now, video one comes from Textbook Tactics, and we're watching the first almost 6 minutes of it. And the second video comes from Krista King. We're watching about 8 minutes of that, starting at the 12-minute mark. Now, I'm adding this commentary in case the videos, when you watch them on your own, didn't make a whole lot of sense, or if you'd like just, my additional comments added to that. But if you felt okay with the two videos on your own, then you don't necessarily need to follow along with me here. So let's jump right in.
This is the Introduction to Trigonometric Identities tutorial. A trigonometric identity is an equality that involves trigonometric functions and is true for all values of the occurring variable. In math, where it's just easiest to show you the work and explain it to you that way. So the first thing...
Okay, so the video kind of paused there for a second. That was my mistake. But anyway, the point he's trying to make here is that with these identities, we're going to use this notion that one side of an equation is equal to another, and we're going to rewrite components of larger equations with these identities. Our goal is to be able to solve trigonometric equations, and in doing so, these identities help us to perform substitutions along the way.
thing you want to start with is the common trigonometric identities. These three groups here are the three most common groups that you're going to deal with. First, we have the Pythagorean identities, and these are the three Pythagorean identities. What you need to know about these identities is simply that the statement on the left is equal to the statement on the right. So, for example, in the first statement here, if you had the cosine squared theta plus sine squared theta, that will always be equal to 1. And
now, you may want to recognize here too that this cosine squared and sine squared in terms of our unit circle represent x and y coordinates. So the reason why we're calling this a Pythagorean identity is that, well, cosine is known as x in the unit circle and sine is known as y in the unit circle. So therefore, x squared plus y squared has to equal 1, or in other words, the radius squared of the unit circle. And what's being done here is you're actually creating a right triangle. So I'm going to go ahead and write down these trig identities for the Pythagorean group. Okay, and let's continue with the video.
what you'd have squared theta, and by the way, you can also substitute x for theta, so you could say...
And sorry for the jumping in the video here. But what he's reminding us is that theta is an unknown variable. Theta represents some unknown angle, and theta is just a letter. It's a Greek letter, but it's a letter representing an unknown. So many times in textbooks or online sites, you might see the letter X used, which is perfectly fine. He's also going to go on to say or talk a little bit more about rearranging these identities in such a way they may be helpful for us in a different problem.
Cosine squared x plus sine squared x is equal to 1. You could rearrange that by, say, subtracting sine squared x from both sides of the equation. And what you'd have is on the left cosine squared x, because the positive sine squared x and the negative sine squared x cancel. So cosine squared x is equal to 1 minus sine squared x.
So that's an alternate form that we might find helpful in a different scenario. So underneath this original Pythagorean equation, I might make another bulleted point and say, well, if cosine squared of theta plus sine squared theta is equal to 1, then cosine squared theta is also equal to 1 minus sine squared theta. Similarly, we can make the argument that sine squared theta, if we had started with sine squared and subtracted cosine over, would be equal to 1 minus cosine squared theta. And again, the reason why this might be helpful is that we might be working with an equation that contains a cosine squared as part of the equation, and it may be helpful for us to rewrite this cosine squared in terms of this grouping over here, or vice versa. Maybe we have this group on the right-hand side inside of our equation, and it might be helpful to simplify that to a single component using this piece on the left. So all of these identities are really just here to help us rewrite larger equations and help us solve larger equations.
Now this is completely common in trig identities. In fact, this is so common, you're going to see this kind of work in almost every problem, where you're rearranging identities. You're not changing them, you're simply rearranging the terms in order to solve the trig identity. So what we did down here can be done with any of these identities, the Pythagorean identities, the reciprocal identities, and the tangent and cotangent identities. I have a little library like this in front of you, a little library of what these identities are. Eventually you're going to memorize them after you've done enough of these problems. However, in the beginning, you really want to have them available to you as you're approaching these problems.
So again, he's mentioning that we could rewrite any one of these Pythagorean identities. For example, up at the top, if we wanted to isolate this one for a moment, we could actually subtract cotangent to the right-hand side, and we would see that 1 is equal to cosecant squared minus cotangent squared, and that's an alternate form that we could add to our list. So we know that 1 is equal to cosecant squared minus cotangent squared. And also, you might hear me saying this too. When I talk about these trigonometric expressions, I often neglect to identify the variable. So let me repeat that again. In this alternate form, we might say something like this, that if I were to subtract the cosecant squared over and try to move the cotangent squared over by itself, then I might have 1 minus cosecant squared equals the opposite of cotangent squared. And again, I'm saying those identities without saying theta or x, and that's pretty typical too as we get into using these more and more frequently.
So after Pythagorean identities, we could look at the reciprocal identities. Now these guys are pretty straightforward. For example, the secant of theta is equal to 1 over cosine theta, the cosecant of theta is equal to 1 over sine theta, and the cotangent of theta is equal to 1 over tangent theta. And again, remember, you can replace the variable theta with another variable such as x. So you could say that the cosecant of x is equal to 1 over sine of x. Now, whatever variable you choose to use, you want to use that variable throughout the problem. For example, you don't want to say the cosecant of x is equal to 1 over sine theta, because that would be confusing. You'd be suggesting that x and theta have different values, and then the identity wouldn't be true.
So that's pretty important. Once you choose a variable for your problem, or once a variable's been identified for your problem, stick with it. Whether they're x's or thetas doesn't matter. Just make sure that you're consistent throughout the entire problem.
So lastly, we have tangent and cotangent identities. So the tangent identity, tangent theta, is equal to the sine theta over cosine theta. And the cotangent identity is that the cotangent of theta is equal to the cosine of theta over sine theta.
Now, all of these are really just definitions that we're already aware of. From the very beginning, we defined secant as the reciprocal of cosine, or 1 divided by cosine. Cosecant is the reciprocal of sine, and cotangent is the reciprocal of tangent. Where this is different is that we're trying to be mindful of the fact that in a larger problem, should we need to rewrite one side of the equation in terms of the other? For example, a lot of our work is easier to solve when we write functions in terms of sine or cosine rather than secant, cosecant, or even tangent. A lot of times we try to rewrite the problem and avoid tangent altogether or cotangent altogether, and instead focus on sine and cosine. So these reciprocal and tangent and cotangent identities, they're really just designed to help us rewrite the problem in a more usable form.
So what I'd like to do next is take a look at some practice problems, and I'll show you how we use these. Let's look at this problem first. What I'd like
Now, before we begin the problem, I need to catch up with my worksheet. So I'm going to pause the video now and update my worksheet by copying all of these identities in place. Okay, so I've now updated my worksheet, and again, these identities are good to reference for future assignments. So it's nice to have them all listed in one simple or one central location here. We're actually going to use these identities now to complete the two examples, and we're going to simplify cosecant x times sine of x. And while it's not explicitly clear, there is an implied multiplication sign here. So cosecant of x times sine of x. As it sits right now, the expression's not too complicated, but we're going to see if we can rewrite it in a more simpler form.
What I'd like to do is simplify this statement, the cosecant of x times the sine of x. So in order to simplify that, we just want to reduce it as much as possible. Now, I know that the cosecant of x is really equal to 1 over sine of x. So 1 over the sine of x. So this is the value of the cosecant of x times the sine of x.
So here's an example of trying to be careful not to mix up your variables. The sample problem or example problem is written in terms of x, whereas our identities were written in terms of theta. So when he's rewriting cosecant of x, he's making sure to write that as 1 over sine of x. So I'm going to do the same here. Cosecant of x is the same as 1 over sine of x, and we're going to multiply that by sine of x, and hopefully you can see where we're going to go next.
So you could write sine of x over 1 if you wanted, and what you'd notice here is if you're multiplying these two, the sine of x is going to cross cancel. So if you simplified this statement, you just simplify it and your answer would be 1. Notice
So that's really the heart of this trigonometric identity stuff. It makes equations easier to work with. So if we're treating this as 1 over sine of x, and this is sine of x over 1, we know that the signs cancel. We're left with a fraction 1 over 1, which is indeed equal to 1. If we were dealing with an even larger problem, a larger equation, what this is telling us is that when we encounter cosine of x times sine of x, we can simply rewrite that as the number 1. And in a way, this is a brand new identity. We've just established a new identity. If we see cosecant of x times sine of x, and we had this in our list of identities, we would know that in a larger equation, we just replace it with the number 1.
how we use the reciprocal identity of the cosecant of theta here, or the cosecant of x, to simplify this problem. Let's take a look at another problem. Let's work with the tangent of x times cosine of x is equal to sine x. What I want you to do is prove this identity. Well, let's start with what we
So to prove an identity, we're just trying to make sure that the left side of the equation does match the right side of the equation. My suggestion usually is to start with the left side and see if we can make it look like the right. And another important tip or helpful idea for these problems is to try to rewrite everything in terms of sine and cosine. So for example, this tangent function, let's try to rewrite that in terms of sine or cosine or both, and then simplify from there. Perhaps something nice will come of that.
know. We know that the tangent of x is also equal to the sine of x over the cosine of x. So I'm going to rewrite that below in the problem here. Tangent of x is really sine of x over the cosine of x. And then we can bring down our cosine x that we're multiplying by. So we have cosine of x here, and this should be equal to the sine of x. Notice we haven't changed the problem at all. I've just substituted a different identity in here for the tangent of x.
I like the way he said that. We're not changing the problem. We're not changing the values on the left or the right hand side of the equation. We're just changing the way the values look. So tangent of x is just being rewritten as sine of x over cosine of x based on that tangent identity. We're going to multiply by cosine of x, and we're hoping that this left side of the equation, we're hoping that all of this on the left is indeed equal to the expression that we were given on the right. Now, if you're looking ahead, you'll hopefully notice that something similar happens here as we saw in the last problem. Imagine that this cosine of x is written over 1. So now this cosine in the denominator and this cosine in the numerator can cancel, and indeed we're left with sine of x over 1, or in other words, that sine of x is equal to sine of x. And we've just confirmed that the left side of the equation in the original problem is indeed equal to the right.
So what you'll notice is that the cosine of x is going to cross cancel here. And what you'll have remaining on the left-hand side is the sine of x. And the sine of x does equal itself. So the sine of x is equal to the sine of x. So in math, this kind of problem here with the equal sign is typically referred to as verifying an identity. So in this case, we verified this identity. The tangent identity in this case, that tangent of theta, or tangent of x, is equal to the sine of theta over the cosine of theta. Let's go ahead and take a look at another problem.
So we're going to stop the video here for his examples, and then I'll just add my 2 cents at the end, and I'll start another video to do the second example, or second video. But what he was saying at the very end is very important as well. You'll see assignment questions that ask you to verify the identity. And what we've done on the right here is an example of that. This is verifying an identity. Again, this expression here could be an identity that's in one of our lists, like we have at the top here. This is a list of a few identities, but there are many, many more. This particular example is another identity, and we've just verified that it is true. We've gone through the trouble using more basic identities to show that the left side of the equation is indeed equal to the right. So therefore, we have verified the identity. And if you haven't noticed, for these types of problems, it's not that the math is very difficult, and it's not that our solution is all that impressive. What I'm looking for, and what we look for as educators and mathematicians, is the proof or the work along the way. So this and this, for example, this is the work. This is the objective of each of these problems, is showing the work and the process that you go through to obtain the final answer. So I'm going to stop this video here and record another one for Krista King's video.